happy Earth Week. It's Earth Week. And it's Dude Be Nice Week, too. Yeah. So, be a nice human. Or, I got another one from my card, too. Ask yourself, have you been kind today? Make kindness your modus operandi and change your world. Yeah. Dude, be nice. You know what's really nice? Ellipses. Ooh. Ellipses are really cool. They actually are pretty cool. So, what an ellipse is. Okay? And that's what we're going to do today and tomorrow. Is we're going to tackle ellipses. Wednesday, Thursday, we're going to tackle hyperbolas. Friday, Monday, we will tackle, like, I'm just going to give you an equation. Here it is. You figure out what it kind of it's going to be. Parabola, circle, ellipse, hyperbola kind of a thing. And then sometime next week, don't know quite what day yet, but sometime next week we'll take a quizzy quiz, testy test on this stuff. Okay? We haven't quite figured out that whole scope and sequence of things yet, but that's what Mod 9 is all about today. So, okay? What else? I don't think I have anything else. We will be using some graph paper today, so if you have your graph paper from Friday, the back side I don't think we even touched yet. Okay? So if not, there's some more up here and all that fun stuff. Alright, so an ellipse. Okay? That blue filled in shape up there, that's an ellipse. Okay? Around the 9-4, I don't even know why I have 9-4 on there yet, because it's not 9-4, it's just ellipse. I don't know if I can do that. Control R. Oh yeah, there it goes. So let's get rid of that one. Whoa, no! Not the whole thing. There. Now I like it. Oh yeah, now I like it. Why didn't it save? There it goes. Now it's saved. Alright? So, what an ellipse is, and I know they can't see this on the interwebs, but you take a circle, okay, and you grab onto one side. Okay? Top, bottom, left, or right side. I don't care which side you grab onto. And as hard as you can, you pull it out. Okay? And that's an ellipse. It's a circle that you took and you either stretched out horizontally, which is what that one looks like, or you stretched it out vertically, which would be that. Okay? Okay? That's what an ellipse is. Okay? Okay? So, here is the, I don't think I have it. Oops. Nope, don't have it. Okay? So here is the, let me get that in full screen. Okay? Oops. Now I do have it. Come on now. The definition, I should say, of an ellipse is, and this is where I don't like this website, I like everything else about this particular site, it's not a curved line. Okay? It's just a curve. Okay? An ellipse is a curve that forms a closed loop. Okay? And the relationship about the closed loop is this. The sum of the distances from 2 points, and we call those points the foci, to every point on the curve is constant. Okay? That's the definition of an ellipse. So, let me increase the size of this one. Okay? So what this is saying, and I have to go over here to the computer to do this now. Okay? So what this is saying is this point is on my ellipse. So length A plus length B is a constant. And every point on this parabola, length A plus length B is always that exact same constant. And so as this point moves around this ellipse, that constant stays the same. The distances to both foci change, but the constant stays the same. It's always that length. It's always that same length. A plus B is a constant. Okay? A and B are changing, but the sum of A and B is always the same. Okay? That's what makes an ellipse an ellipse. Yeah? So, the nice thing is, when we had circles, we started with circles, we had one equation. Okay? Then we went to parabolas, and we had two equations. For left and right parabolas, we had one equation. For up and down parabolas, we had another equation. Okay? For ellipses, we're going back to one equation. Oops, no, I can't necessarily, come on now. Changing colors on me. There it is. Okay? So we're going back to one equation. And that equation is this. The quantity x minus h squared divided by a squared plus the quantity y minus k squared divided by b squared is equal to 1. Okay. The one condition that we have is that a cannot equal b. Because if a does equal b, then it's a circle. Okay? So if a is not equal to b, it's an ellipse. If a is equal to b, it's a circle. Okay? But we'll get more into that later on this week as to how you can tell without even looking or without even doing all this, getting in this form, how you can tell which one is which. Okay? All right. So here are some examples of ellipses found in the real world. Okay? Orbits of interstellar bodies, okay, are usually elliptical in their shape. Okay? If you take, you got a camelback, Kelsey's got a camelback, okay? If you take a glass, and it's hard to see because hers is full, but if you can see through and you tip it to the side, okay? If you tip it a little bit like that, the water, here now it's circular when I'm vertical with it, but if I tip it to the side, now it's elliptical. Okay? The roof of some buildings, okay, this one in particular, is an ellipse. Orbitals of electrons and protons and all that fun stuff around atoms, that's elliptical. Billiards, okay, some billiards table is an ellipse. Okay? Billiards is different than pool, just so you know. Okay? Pool has pockets, and you try and get the balls into the pockets. Billiards doesn't have pockets. Billiards is all about angles and geometry, and you got to hit a certain amount of sides before you can touch your ball, depending upon where your it's cool, yeah. But these other two, this one on the right here, that is St. Paul's Cathedral in London town, okay, London, England. Okay, there's that one. But this one over here on the left is probably the coolest. Okay, this is the first chamber of the House of Representatives of the United States of America. Okay, and what makes it cool is this story. Okay? In this room, John Quincy Adams, and you guys have all been through History 1, U.S. History 1, you probably know who John Quincy Adams is. Okay? He was one of the historical people in this country. Okay? While he was a member of the House of Representatives, he discovered an acoustical phenomenon. He sat his desk at the foci of this elliptical room. And by doing that, he was able to eavesdrop on conversations going on at the other foci. Okay? So basically what he did was he put his desk at F1. And then he could hear all the conversations going on around F2 because of the acoustics and the sound waves bouncing off, following path B here, bouncing off the stone walls of the room and coming back then to F1. Okay? There's a room, I think there used to be, I haven't been there in many, many years, but at the Science Museum in St. Paul, Minnesota, there's a room like that where you can stand at one of the foci in this elliptical room and talk to, so if I'm standing at the one foci and Luke's standing at the other foci, we can have a conversation about this volume, but we're 150 feet apart, and there's other things going on in this room. It's pretty sweet because it just is how the sound waves bounce off and the relationship between the foci. So it's pretty cool kind of historical fact. So people the members of Congress at the time couldn't figure out why does John QA know everything that we're doing? You know, well, here to find out, he's listening in. He's not doing any talking, so they can't hear him. He's just listening. He looks like he's working, but he's really just listening, eavesdropping on their other conversations. So. Pretty smart. Okay. So that's an ellipse, right? Okay. What's the first thing you think that we're going to have to do with this ellipse?
Find the center.
Find the center. Yep. We're going to find the center first. How are we going to go about finding the center?
2 points above AB. Or 2 things above AB.
Okay, 2 things above A. So what's attached to the X and what's attached to the Y? So it's kind of like circles, right? We see that in circles? How do we do it in circles? What was the kicker for circles? We said something about something. How do we find H and K? So it's just like with circles. We want to identify the center. What is the center here?
30, -2.
How'd you come up with 3 and -2? Because I see -3 and +2.
So when it's X, or it's X minus 3, but it's in the parentheses, so then you would think the opposite.
So we think oppositely inside parentheses. Inside a set of parentheses, we think oppositely. So just like with circles, just like with ellipses, we think oppositely inside a set of parentheses. So the center here would be 3, -2. Okay? Whatever is subtracted or added to the X is the X part of our center. Whatever is added or subtracted to the Y is the Y part of our center. Okay? So, now that we know where the center is, let's graph it. 3, -2 is right there. Now I'm going to put a little C by it because technically it's not on my ellipse, but I'm going to use it because everything's going to flow from the center. Okay? So, then, next. Whatever is underneath the X, that's what I'm going to look at. So in this case, I'm going to look at the 9, because 9 is underneath my X squared. Okay? I'm going to take 9, and I'm going to square root it. So the square root of 9 is 3. Okay? So because it's underneath X, that tells me that I am going to go 3 to the left and 3 to the right of my center. Okay? And that's going to give me the endpoints of one of my axes. Okay? In an ellipse, there are 2 axes. There's a vertical axis of symmetry, okay, that I can fold my ellipse over, and there's a horizontal axis of symmetry that I can fold my ellipse over. Okay? So that's the endpoints then of my horizontal axis of symmetry. Okay? Good so far. Okay? So let me get up to speed here again. So there is my center. 1, 2, and 3. 1, 2, and 3. So there's where we're at right now. Okay? Now I'm going to do the exact same thing, but now I'm going to look underneath the y term. Okay? 16 is underneath the y term. So now that's going to tell me I'm going to take the square root of that. Square root of 16 is 4. So I'm going to go up 4 and down 4. That gives me the endpoints of my vertical axis of symmetry. Okay? Right? With me so far? Now, what I can do is, that's the framework for my ellipse, so now I'm going to draw it in. Oops, went a little too far. Okay. Now that I have it drawn in, we're going to take those two axes of symmetry and we're going to rename them. Okay? We're going to rename them into, one of them is going to be called the minor axes. And the other one is going to be called the major axes. Okay? How do you think, from my picture, that I can determine which one's the minor one and which one's the major one? Minor is the shorter one. Okay? So in this particular case, the minor axis is going to be the shorter of the two. Okay? So whichever one, the vertical or the horizontal one, is shorter, that one's called the minor axis. Okay? And just based off of the nature of it, because it's minor, okay, that's all we need to know. We just kind of need to know which one it is. Okay? It's the major axes that is where all the action happens. Okay? So, how do you think I'm going to determine which one's the major axis? It's the other one or the longer one. Now, we just determine which one's the major axis for two reasons. One, the foci are on the major axes. Okay? So that's one reason that we need to determine which one's the major axis, because that's where our foci are. Okay? The second reason that we determine what the major axis is because there are things called the vertices of the ellipse. There's two of them. The vertices are the endpoints of the major axis. Okay? So we determined already that in this particular case, the major axis is vertical or horizontal? Vertical. So that means that this point right here, 3, positive 2, and this point right here, 3, negative 6, are the two vertices. Okay. And we also know that our foci are going to be somewhere along that vertical axis of symmetry. Okay? So, let's find the foci now. Okay? Let me get back up to speed here. Here is my center. There is that one. There is that one. There is that one. There is that one. Those two are also the vertices. Ooh. Ooh, don't like it. Kind of looks like lurch. I lurched it a little bit. Lurch, of course, from the... Very good. Okay. Adam's family? Yeah, I heard it. Yeah, teacher hearing. Yeah. 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 All right. If you prefer Hunchback of Notre Dame, we could have done that. Is that Quasimodo? Was he the Hunchback of Notre Dame? Yeah? I think so. Okay. So don't Quasimodo it. Okay? So the last thing we need are the foci. Foci is the plural of focus. Okay? In a parabola, there was only one focus because there was only one curve. Okay? In an ellipse, there's two foci. Okay? All right? And those are that F1 and F2 points of here. Okay? F1 is the first foci, or first focus, and F2 is the second focus. Okay? So there's two focus, or two foci. Okay? Located on the major axes, we talked about that in the last slide. Line across the ellipse that is stretched out the most, so the longer one. Okay? The most important formula for foci is c squared is equal to a squared minus b squared, or the absolute value of a squared minus b squared. Okay? C is defined as the distance from the center to each foci, okay, to each focus. Okay? A squared is the number underneath the x term. B squared is the number underneath the y squared term. Okay? That comes from our equation. Okay? But C is that distance to the focus.
Did you say that for radius?
No, because it's not totally circular.
Did you say like radius?
No, because sometimes it's horizontal, sometimes it's vertical. So that's why we just call it the distance to the focus. Okay? Okay? So in this particular case, a squared was 9, b squared was 16. Okay? So a squared equals 9, b squared equals 16. Yeah, my installation failed. Come on, you're in the way. Clear, clear, clear. There it goes. Okay? All right? So 9 minus 16 is negative 7, right? Absolute value of negative 7 is positive 7. So c squared is equal to 7. Which means c is equal to what? Square root of 7. Okay? Alright? So, and that, now because we said that our major axis was vertical in this case, so we're going to add the square root of 7 to the y part to get where the upper foci is, and we're going to subtract it from the y part of our center to get where the lower foci is. Okay? So because our major axis is vertical, I'm going to add the square root of 7. What is the square root of 7? 2.7. 0.6-ish? Okay, sure. I mean, I'm just guessing here. So that puts it right there, and then it puts it right there. Okay? In mathematical terms, we're going to write that as 3, comma, negative 2 plus or minus the square root of 7. Okay? Or, if you wanted to write each one out, you could write them out. Okay? I had told you last week that if this were an ellipse problem, I would ask you for the vertex, the axis of symmetry, the directrix, and the focus. Those 4 key things along with the graph. In an ellipse, I'm going to ask you not only to graph it, but I'm going to ask you for the 5 key points. Okay? The 5 key points of an ellipse are the center, the 2 vertices, and the 2 foci. Okay? So if this were a problem for a quiz at some point in time, and I said graph this ellipse, I'm going to ask you then for the 5 key points. Center, 2 vertices, 2 foci. Okay? Let's try another one. I like that one. Okay. So, step number 1 said we needed to find the center. Where is the center? Do we agree with 1 comma negative 2? Step 2 said what? So right and left, I'm going to go 5, right? Now, 1, 2, 3, 4, 5 is that point right there. Let me get rid of that extra dot that I threw in there. Okay. 1, 2, 3, 4, and 5 right there. Now, my question to you is this. Which one is going to be the major axis? Just by looking at the equation. Horizontal is going to be a major axis. Why? But just by looking at the equation.
The term underneath the x is larger than the term under y.
Yep. Bigger number underneath x. Wherever the bigger number is, that square root's going to be bigger. Okay? Because you're square rooting both of them. So wherever the bigger number is, that's going to be your major axis. So those 2 points are not only the endpoints of the horizontal axis of symmetry, but they're also the vertices. Yep. So that is going to be at what? Negative 4 comma negative 2? And positive 6 comma negative 2? Yes? Okay. Then I'm going to look underneath the y. How many am I going to go up or down from my center? 2. So there's that. Now I can draw it in. Oh, nope, don't like it already. Oh yeah, that's a good one. That's a good one. Brought out the A game on that ellipse. Okay. And lastly, what we have to find is we have to find our foci. So this is how I do it. So I go on the side here, I go c squared is the absolute value of 25 minus 4, a squared minus b squared. 25 minus 4 is 21. Absolute value of 21 is 21. So c squared is 21. So c is the square root of 21. Okay? And we're going to leave it in simplified radical form. Okay? If we would need to graph it, then we would, adjust it. We would adjust that to, because what's the square root of 21? 4.7-ish? Yeah? 4.6, 4.7, somewhere in that range. So that puts my focus there and there. Okay? So my foci then are going to be at, because I'm adding it to the x, because it's horizontal, it's going to be 1 plus or minus the square root of 21, comma, negative 2. And I can leave it just like that.
So when it's horizontal, you have it in the x term, and it's vertical, you put it in the y term.
In the y term. Yep.